So good afternoon. Our speaker today is Yunwei Deng, who's a third-year PhD student at the University of Tsinhgua at the Department of Astronomy. His supervisor is Professor Hui Li, and he works on cosmological simulations of dwarf galaxies at high redshift, including stellar feedback from individual stars. And in this semester, he's visiting Federico Marinacci, who's not here today because he has to teach, until the end of November. So please, take it.
Thank you, Franco. Good afternoon, everyone. I'm Yunwei Deng from Tsinghua University, and I'm a third-year PhD student working with Hui Li. And currently, I'm visiting Federico Marinacci at the University of Bologna until the middle of November. I'm very glad to be here to have this chance to present our work. So today I will talk about our RIGEL model for multiphase ISM and the feedback from individual massive stars. So it's basically a new galaxy formation model, galaxy formation ISM model based on the areport code, also the areport RT because they have the radiative transfer. So the title of my talk is simulating dwarf galaxies with realistic ISM using the RIGEL model. So at the beginning, I want to introduce that dwarf galaxies actually provide an ideal test field for galaxy formation models. And here is a long-standing tension for the between the observations and the numerical simulations of dwarf galaxies, the mass metallicity relation of the ultra-thin dwarf galaxies. So these dwarf galaxies located in the lowest mass dark matter halos, and the gray crosses here are the observations, and the colorful dots are various numerical simulations. And you can see for the smallest dwarf galaxies, especially these with halo mass less than 10 to 9 solar mass, the observed metallicities are significantly higher than what simulations predicted. Up until 2023, no simulations have successfully expanded this discrepancy. However, we have some possible solutions. Firstly, on a large scale, ultra-thin dwarf galaxies are highly sensitive to the background UV radiation during the reionization epoch. So their star formation history can vary depending on their relative position to their nearby massive halos during the epoch of reionization. So with cosmological reionization simulations like THESAN-ZOOM, THESAN-ZOOM, we can simulate a more realistic inhomogeneous UV background during this epoch. And for example, recent work by Kim et al. Has shown that even a very coarse patchy reionization treatment, basically you still use a uniform UV background, but you can tune in the amplitude of this background based on the environment. So even this patchy reionization treatment can alleviate this tension significantly. Therefore, it's promising that using this more realistic cosmological reionization simulations, we can further address this issue. And secondly, on the small scale, improving the feedback model is also crucial for solving this problem. For instance, the Wheeler simulation, maybe this yellow dots has extremely low metallicity for these ultra-thin dwarf galaxies. This is likely due to the overly strong feedback and this overly strong and very disruptive feedback in the fire model. So this is where our RIGEL model comes into play, offering a significantly better feedback model. So combining our RIGEL model with such large-scale cosmological reionization simulation like THESAN, we can do cosmological zoom-in simulation with our more detailed RIGEL physics, and may eventually address this tension. But this is actually what I will done in the next years for my PhD thesis project. But it's still at a starting stage currently. So today I will more focus on the performance of my RIGEL model in non-cosmological simulations. Firstly, I will try to use this slide to convince you that on small scale, radiative feedback from stars is important. Consider this example: the observations of very young clusters like NGC 602 reveals a very rapid disruption of its natal GMC. Such a rapid disruption cannot be attributed to the supernova feedback because this cluster is too young to have any dead star. So the radiation and the stellar wind feedback are the only solution. And it turns out that radiative feedback provides comparable or even more feedback budget than the supernova explosion. And consequently, the time scale for molecular clouds in star forming phase is very short, only several megayears. And if you count the age of stars in young clusters, you will find the age spread of the member stars are also very short, maybe less than 4 megayears, like the ONC cluster. And zooming out to a galaxy scale, recent observation of the spatial decorrelation between the GMCs and the H2 regions or young clusters in nearby galaxies have also shown that the time scale of feedback dispersed in GMC is maybe as short as 1.5 megayear. So when our simulation are going to resolve the star forming ISM in great detail and resolve star clusters, we must capture these observed properties of star forming clouds and star clusters by the more realistic modeling of stellar feedback and the ISM physics, especially the radiative feedback and its impact in the ISM, right? So to accurately capture these small-scale effects in dwarf galaxy simulations, recent state-of-art dwarf galaxy simulations have achieved an extremely high resolution of several solar mass. So at this level of resolution, individual stars can be resolved and allowing us to track their evolution and the feedback, multi-channel feedback directly through various channels, star by star. So this simulation also incorporated highly detailed ISM physics, including gas cooling, heating, dust physics, and the complex chemistry, etc., etc. However, it is important to note that in all these simulations I presented here, the radiative feedback from stars is still modeled using some approximation methods, like the stringent type method approximation, rather than by explicitly solving the radiative transfer equations on the fly in your simulations, right? So the first major highlight of our RIGEL model is that it used RT to conduct high-resolution simulations with on-the-fly radiative transfer, also at the solar mass resolution level. So I want to emphasize that performing RHD radiative radiation hydrodynamic simulations, or say RHD simulations at this high resolution is not as simple as just turning on the switch of RT, so or other radiative solvers. So this is because the spatial and the temporal scale of individual H2 regions are quite small, only several solar mass in size and just hundreds of years in time. So, also more importantly, these two scales are both inversely proportional to the density, where the stars are all formed in very dense gas. So this equation tells us typically we can only resolve the initial stringency field of an individual star if the density is smaller than 32 per cc. So this tells us that the initial phase of H2 regions is hard to be resolved, but as the H2 regions can expansion as and the density goes low along with its expansion, the later phase can be easy to be resolved. Therefore, we need to deal with the unresolved initial phase of H2 region, and this is what my first paper in my life has done. that we studied the impact of numerical resolution on the ionization feedback from young massive stars, and we found that the feedback can be enhanced when the spatial resolution is insufficient or is low, but be reduced when the temporal resolution RCO is low, RCO information time step is too large. The feedback will be reduced, and we analyze the physical reason of these numerical issues and provide some practical method to correct them. So, but I may skip this work because of the time. So anyway, now the RT is ready for high resolution simulations after this work. And the second highlight of RIGEL model is that we updated the low temperature cooling model of RT. So the low temperature cooling here refer to lower than 10⁴ Kelvin. So here I use the low temperature cooling model using by Battiferro as the configuration, which determines their cooling rate based on some fitting function based on pre-calculated cloudy results. So the problem is that these cloudy results, fitting function of cloudy results, cannot cover a sufficiently large parameter space of metallicity, density, temperature, radiation field, all the SM parameters. So they are biased in a narrow parameter space. Now, as we have the on-the-fly RT, we can determine the exact ionization state of the main ISM coolant, not only the primordial elements like hydrogen and helium, but also the abundance of this C+, OO+, and CO, this main ISM coolant in the neutral warm medium. So as you can see, for example, our more physical model has a clear metallicity dependence. With 10 times lower metallicity, there are maybe 10 times lower, or roughly 10 times lower cooling rate. But for Battiferro, it is almost the same, especially for the 0.1 solar and 0.01 solar metallicity. It's almost the same cooling rate. So consequently, this figure shows the result of an isolated of two identical isolated dwarf galaxy simulations. The only difference is that I use different cooling model. One green is Battiferro and black is RIGEL. So you can see with 10 times lower cooling rate, I get 10 times lower star formation rate, which gives us the implication that the star formation rate in the high redshift mantle pole dwarf galaxies may not as bursty and destructive as Battiferro predicted. So, so the last part is that we have now our code is ready, and but to modeling the stellar feedback, we need a more accurate stellar feedback model. So to do this, we model the stellar feedback star by star by sampling individual massive stars from the MF initial mass function, and we compile the library of radiation and the wind properties as a function of the star's initial mass and the initial metallicity. So basically, you can see more mantle pole stars are brighter, and vice versa for the wind property. For given mass, more mantle pole stars has weaker wind. So maybe everyone knows these trends, but only a few of models have considered the metallicity dependence of stellar feedback intensity. You can see there are orders of magnitude differences. So based on our library, we can use polynomial fitting functions to decide the radiation and the wind properties of each individual stars in my simulations on the fly. Okay. So now with all these updates and the implementations, we can finally simulate dwarf galaxies with on-the-fly radiative transfer, metallicity-dependent stellar feedback, and they are from individual massive stars. So we launched the RIGEL project. So at the beginning, we tested the performance of RIGEL in long course module simulations like these isolated dwarf galaxies, and this merger of two identical dwarf galaxies is a major merger. So, and we also have a project to study the star formation in the central molecular zoom of the Milky Way, leading by Li Zhi, my collaborator. So First of all, this is the Kennicott-Schmidt relation in the simulated off-axis. So the right points are from yeah. To close this. Okay, so you can see the legend here. So the right points are from the metal poles of galaxy initialized from 0.02 solar mass metallicity. And the green dots are from 0.2, a little bit metal rich one. And lastly, the blue points are from a simulation without any radiative feedback, labeled as no RT, means there are no radiative transfer and no radiative feedback. So you can say both the mantle pole and the mantle rich full feedback galaxies are consistent with the observed Kennicott-Schmidt relation and the Anna Green's star formation relation fitting function, where the no RT simulation shows a higher star formation surface density at a given gas surface density. So it means that radiative feedback do reduce the star formation rate to observed level, and the left panel. So the left panel is the relation between the star formation. No, it's right panel. The right panel is the relation between the star formation surface density and the ISM total pressure. So to read this figure, if you see it vertically for a given pressure, the full feedback run has a higher star formation rate. And the no RT run has a higher star formation rate, and the full feedback run has a low star formation rate, which means the radiative feedback as an additional feedback channel reduced the star formation efficiency, as I said. And for a given star formation rate, if you look this figure horizontally, for a given star formation rate, you can see the full feedback run has a higher ISM pressure, which is simply you provide additional feedback channels, radiative feedback, you get higher thermal pressure for the ISM. So interestingly, what is interesting is that when we submit this paper to archives, we found that we compare our results with Ostraker and Team's 22 results, and found that their result shows a higher star formation rate compared to ours, and it matches with the no RT results. However, just maybe 4 months ago, Kim and Ostraker, they submitted another paper and provide some metallicity dependent new fitting functions for this relation. And you can see our results consistent with theirs very well. So it's some robust result. Okay. Yes. So the real now I will talk about the cluster formation, star cluster properties in the RIGEL simulations, which is also an achievement of our RIGEL model. So this figure shows the star cluster initial mass function in the isolated galaxy. You can see both the full feedback runs, the green and the red curve, has a steep slope with a power law index of -2, which is consistent with the observations, whereas the no RT run has a flatter cluster mass function, which means there are more massive clusters in the without the radiative feedback. This tells us that radiative feedback plays a role in prohibit the formation of massive clusters. And another figure shows that the relation between the maximum cluster mass in the galaxy and the galaxy-wide star formation rate from merger simulations. So the green dots are the observations, and the colorful dots are its relation from different type from the merger simulation. So basically, it's a different merger stage. And you can see the star formation rate covers maybe 3 orders of magnitude. And our simulations captures this observed relation nicely, which is very important for dwarf galaxy simulations, because the star formation rate in quiescent dwarfs are very low in most times, and only when the dwarf galaxy gets into some merger or starburst, they can have a high star formation rate. So in the quiescent period of the dwarf galaxies, massive star clusters cannot be formed. But if your galaxy formation model just sample the cluster mass from the cluster mass function, you may stochastically get some massive star clusters during the quiescent phase of your galaxy. But our model avoid this problem by capture the self-regulated small cluster formation. So here I have a movie to present you how radiative feedback plays its role on disrupt molecular clouds early. So this is a temperature slide of a phase-on patch of our fiducial galaxy. So the blue clump is a cold molecular clouds. And it's a temperature slice. Let's play it. And as the time goes, a massive star formed there and provides the H2 region feedback. And the supernova comes very late, and the molecular cloud has already been disrupted before the supernova explosion. So supernova has nothing to do with the molecular cloud disruption, and the H2 region feedback, radiative feedback, do all the things. So this phenomena is not unique in my simulation. So this figure shows the relation between the formation time of the first to last member star of each cluster, basically the H spread, and the x-axis is the formation time of the first massive star in the cluster. So the diagonal lines means that the time when the first massive star formed is exactly the time when the cluster stopped forming new stars. And you can see for the full feedback rounds, this difference of these 2 times are within 1 megayear, means that the formation of massive stars can rapidly stop the further star formation because it's already dispersed the GMC, whereas it's not true for the blue dots, the non-RT rock, because they need to wait for the supernova explosion. So at larger scale, galaxy outflow is also of great interest for our model, for our simulation. For example, to investigate whether the radiative feedback plays a positive role or negative role on launching galactic outflow, we run a new suite of simulations, and we set 3 different initial conditions with the same total mass, total dark matter mass, and the same total baryon mass. So the gravitational potential is the same, but we set different ratio between the stellar mass and the gas mass. So the total baryon mass is the same, 10 to 8. And G90 means that there are 90% gas and 10% star. G50 means there are 50% star, 50% gas, and G20 means 20% gas and 80% stars. So in total, 6 simulations, 3 different initial conditions, and with and without radiative feedback. So this is the results, the mass and energy loading factor of these simulations. So the full feedback counts in black and non-RT in red. And for you can see for the low gas fraction G20 galaxy, the full feedback rounds has higher loading factor. Whereas on the other hand, for the G90 galaxy with high gas fraction, the full feedback has lower loading factor. And G50 is the intermediate stage. So you can see in high gas fraction regime, radiative feedback plays a negative role on launching gas outflow, while in low gas fraction regime, it plays a positive role. And we can also compare this with observation and get this trend which matches over the observations of dwarf galaxies. So finally, I will use a few minutes to introduce what I'm doing with Federico in Bologna now. So basically, I'm running a simulation of the merger of 2 identical dwarf galaxies. So I run it for 200 meg years, and I analyze these results by stages. I have 4 stages: approaching first peak, which means the merger introduced the starburst peak, and the plateau stage, and the second peak, which is the highest peak. So what I want to answer is that whether the galaxy-wide starburst in merger system is driven by an enhanced cloud-scale star formation efficiency, or just by increase the gas supply during the merger, or the combination of these 2 factors. So to study the star formation at cloud scale, first I need to identify the clouds. So I use the cloud founder code, which is basically a subfind algorithm in Python. So I identify clouds by the threshold of dense than 10 per cc and the Weir parameter less than 10. And this is an example. The blue are the black circles are the cloud, and this is the cloud mass function. You can see during the merger, I have a more flatter cloud mass function, which means I have more cold cloud for star formation. Indeed, we have more gas fuel in merger. But what about the star formation efficiency? I will jump to the last slide to see this. So I studied the integrated star formation efficiency for each individual clouds. So basically, it's defined as the ratio between the total stellar mass formed during the entire life cycle of a cloud over the total baryon mass of this cloud during its entire life cycle. So previous studies suggest that this integrated star formation efficiency has a relation between with the surface density of the clouds, and which is the green line. It's a positive relation, and it's saturated at very high density. But what I found is that in the approaching, which is more isolated stage, and in the merger stage, there are no significant difference on this relation. The distribution of SFE on this plot are the same. So we can say that the merger enhanced the star formation efficiency. Especially, you can see here are some very dense gas clouds in this figure there, but they do not have a very high star formation efficiency. And I want to understand why, and I first checked the influence of the tidal field. So this figure is color coded with the tidal strength of the tidal field strength of the clouds, and I don't find any significant difference for these clouds to explain why they have a low star formation efficiency. So it's still under investigating with Battiferro. So that's all. Thank you. Thank you for your attention.
Questions for the speaker?
This is not a summary, sorry.
Yes.
So I have just a question regarding the new cooling function that you implemented in the simulation. So you were showing that this obviously has an effect on the star formation history, or some like the star formation history there. So I was wondering whether I understand the fact that with the RIGEL cooling, you have a lower overall star formation rate because you cool less. That's if I'm correct. But do you have an idea on the impact on the flickering, so on the burstiness of the galaxy? Because this is something that has been discussed a lot now in the literature for high-redshift galaxies. So the impact of this burstiness, especially possibly in low metallicity environments. So do you have, I mean, by looking at the plot, it seems that more or less the up and down are similar.
Yeah, for the burstiness, I want to say for the isolated galaxy that it's hard to quantify the burstiness in such an isolated configuration, because in the isolated galaxies you can see the star formation rate is overall very steady, even though that they have some up and down, but the mean value is very steady. But I think what the galaxy formation community concerned is that the dwarf galaxies may have some very large scale. We have some bursty performance on very large time scale. Maybe they may want to see some star formation history like this, with some burst on 100 million-year scale. This is not the thing the isolated dwarf galaxy simulation can answer. But as I introduced at the beginning and what I will show at the end, I'm planning to run cosmological simulations with the RIGEL model. For example, I want to run a 10 to 9 to 10 to 7 solar mass halo to study the cosmological evolution of local dwarf galaxies. In this case, we can finally see whether it has a bursty star formation on a cosmological evolution scale.
So I had a question about that indeed. So what exactly do you expect to see changing in the cosmological case? I think you will have mergers, continuous accretions. So where do you expect the most change in everything you showed us, going from non-cosmological to cosmological simulations?
So basically, what I want for cosmological simulations, the most exciting scientific question I want to solve is this mass metallicity relation. But for isolated dwarf galaxy, you can never research this because you have to set an initial metallicity. But for cosmological simulation, I can start with zero metallicity news, see what it evolved, right? So this is, I mean, and also the stellar mass halo mass relation and the size stellar mass relation, all these scale relations, they all have some tensions between simulations and observations, and this is what can be resolved in our cosmological simulations.
Other questions? Yep.
Since we were talking about the cooling function, I do appreciate the behavior of yours because basically you're looking at the 10 to 1000 Kelvin. This is where basically the cooling function is dominated by the carbon line. I don't, so I totally understand it. You drop metallicity by a factor 10, the cooling function goes down by a factor 10. There's less carbon. But I don't understand actually the fire result that don't see this.
This is mathematically I can tell you why. Because you can see the metallicity in their fitting functions appears here. And there are one plus factor here. So if you have an extremely low metallicity, it's converged to 1 because it's 1 plus effect. So I don't know why they use this function, but this is what they are using.
Other question?
At the end you showed how the mass function of the clusters change in the merger simulation, and you were showing how it evolves in the different phases of the merging. I was wondering, I see the comparison with some slopes, but I was wondering if you had tested if there is a change only in the massive clumps that you are forming, or also a change in the slope. Is the slope getting smaller, so a flatter mass function when you are really at the peak of star formation, or you have just the same slope but just extending at larger masses?
I didn't quantify the slope, but by eye, I guess there are some difference because maybe you can see the blue and the purple lines. So recall that blue is during this stage, the plateau with relatively low star formation, and the purple is maybe 100 times higher star formation rate. And by eye, I can see some difference in slope, right?
Okay.
Okay. Any more questions? No? Then, okay. Thanks, Rod.
Thank you.